What is Verilog and what is an FPGA? Well, Verilog is a sort of programming language in which you can describe digital circuits. An FPGA is a type of integrated circuit chip. It's a blank configurable chip on which you can implement pretty much any digital circuit. Verilog is a type of hardware description language, or HDL. There are two important hardware description languages, Verilog and VHDL. In this video, we'll be talking about Verilog. The Verilog language has evolved into System Verilog, but the distinction won't be important to us. This video will provide an overview and an introduction to Verilog and FPGAs, and we'll work through a simple example circuit. All right, let's get started. Sometimes hardware description languages are referred to as programming languages, but I'm really not comfortable with that. I mean, there are some clear similarities. Comparing Verilog to a language like C, you create a text file with your editor, and both of them have syntax with, semicolons after statements and so on. And then you compile both your program and your Verilog design. But that is where the similarities end. In the case of a programming language, the compiler will produce an executable file, which can then be loaded and run on the computer. In the case of a hardware description language, the compiler produces a circuit description, and that's kept in files. And with that circuit description, you can do several different things. In one case, you can simulate it with some other software to verify that your circuit works as you expect it to work. If you have a lot of money, like Intel or another company like that, you can fabricate the circuit in custom integrated circuits. But what most likely you would do as a hobbyist is to load your circuit onto an FPGA, and then once your circuit has been downloaded onto the FPGA chip, you can then power up and use the circuit. In this video, we're going to look at serial communication. This is sometimes known as RS-232 communication. And it's a way for two devices to communicate using three wires, one of which is ground. So there's a transmit connection and a receive connection on each of the two devices. If you are familiar with Arduino, the transmit and receive signals are available on pins 1 and 2. And every time you do something like a serial.print, you will transmit on the transmit pin. Of course, the Arduino also sends the communication over the USB connection, and you can see it in your serial monitor window, but that's another story. The communication channels send 1 byte at a time, and since this is a single wire, each bit has to be sent individually. And the two transmission pathways are independent. So the transmit circuit and the receive circuit are independent. Well, they may share a system clock or something like that, but you can be transmitting simultaneously in both directions. And in that sense, it's said to be full duplex. To describe how bytes are sent over a serial communication channel, let's look at sending the uppercase K. In ASCII, that's 4B, or 01001011. The bits are sent in reverse order, so we send the least significant bit first, followed by the more significant bits. Here's a waveform that shows what is sent over the wire from the transmit to the receive channel. Before the byte is sent, the wire will be high in the idle state, and then we'll send a start bit, which is a 0, followed by the data bits, 1101, 0010. And finally, we'll follow that with what's called the stop bit, which is high. And the stop bit is essentially the beginning of a long period of idleness, and so we're guaranteed that the idle period will be high at least for 1 bit duration. So here I repeated this waveform and showing voltages at TTL levels. So we have 0 bit represented with 0 volts, and 1 bit represented with high TTL voltage levels, which I've symbolized with 5 volts here. Now, there was something else called the RS-232 standard, which is very similar in terms of how the bits are sent and the start bit and stop bit and so on, but the voltage levels are a bit different. In fact, these voltage levels can range as high as plus and minus 25 volts. And so you definitely don't want to connect something that's using the RS-232 levels into TTL circuitry, or else you'll fry your chips. And the other thing about the RS-232 levels is that things are reversed. So a 0 is sent as a high voltage and a 1 is sent as a low voltage. We don't see the RS-232 levels too often, but you may have to interface to old equipment. And there's a nice little chip that will interface between these voltage levels. If you use the Arduino on pins 1 and 2, you'll see these TTL levels. With serial communication, each individual party may have its own internal clock, but there is no shared clock signal. So the question is, how long are these bits? What is the timing here? And that's a question of baud rate. There are several common baud rates. 9600 is a common baud rate. And it means that 9600 bits are sent every second. Well, every time you send a byte, you have to send a start bit, a stop bit, and the 8 data bits. So that's 10 bits total. So at a baud rate of 9600, it means you're sending 960 bytes per second. So the baud rate has to be agreed on by both parties in order for the serial communication to work. They also have to agree on the number of stop bits. We used 1 stop bit here, but sometimes there'll be 2 stop bits. We can also insert a parity bit, and sometimes we send bytes that only have 7 bits in them. That's pretty uncommon anymore. So what I've shown here is something called 8 in 1, meaning 8 bits in each byte, no parity bit, and only 1 stop bit. Here I'm showing a timing diagram in a traditional way. And we have an idle period where the signal is high, and then we have a start bit where the signal is low. And then for a number of periods, we have the 8 data bits, followed by a stop bit where the wire will go high and will stay high for at least 1 bit length. Now, our system will have an internal clock, and this clock will be running much faster. And so we will basically have a circuit that samples the wire at different times to determine what's going on. So it will be sampling the wire continuously until it sees it go low. And at that point, we have the beginning of the start bit. Now there could be some noise here. So the minute the line goes low, we basically start counting using our internal clock until we get to where the middle of the start bit should be. And at that point, we check to make sure the line is still low and that it really was a valid start bit and not a glitch of some sort. And then at that point, we start counting. And each bit duration will mark the bit. And so we're at the middle of the bit here, and we count 1 bit time, which will put us in the middle of the first bit, and then 1 more bit time, which will put us in the middle of the second bit, and so on. And then finally, we are in the middle of the stop bit, and we should be seeing a high line. And at that point, we go back into the idle mode, where we're just constantly looking for the beginning of a start bit. So we've got some internal clock, and we can measure the length of each one of these bits. And we'll call, using a variable, we'll call it clocks per bit. Okay, so we will be using a baud rate that's quite high, 230,400 bits per second, and we'll be using a clock rate of 125 megahertz. So we can calculate our clocks per bit, okay, 125 million divided by this baud rate, and that gives us a number. We'll round it to an integer, and so our clocks per bit will be 543. So that will give us enough accuracy to measure the center points of all these bits. and we won't have any problems, significant problems with skew within the 10 bits that we'll be looking at here. We're going to describe two circuits, one for the receive channel and one for the transmit channel. Here's a block diagram for the receive circuit we wanted to design. The primary input is connected to the receive channel and also has a clock input. The 8 data byte lines will be valid after we receive a byte, and this data available line will go high to indicate that we have actually received a byte. So looking at the timing diagram for this thing, we see the system clock down here, and after the byte has been fully received, the data available output will go high for 1 clock cycle, and during that clock cycle, the data on these 8 lines will be valid. Here's a block diagram for the transmit circuit we want to design. By the way, this acronym UART stands for Universal Asynchronous Receive Transmit, and that's always associated with serial communication as we're describing it here. The primary output is connected to the transmit channel, and the way it works is the byte that you want to send are provided on these 8 inputs, and the data available signal is pulsed once, and at that point the circuit will then begin sending the byte. And it also has 2 outputs to indicate whether it's busy, that is active, sending a byte, or not. And then once the byte has been sent, it will pulse this done line exactly 1 clock cycle. So let's look at the timing diagram for this. Here's our system clock at the bottom. And to get this thing going, the larger circuit will provide data and pulse the data available line for 1 clock signal. And after that, whatever was on the data lines will be ignored. Our circuit will latch this into a register, and then the active line will become high, and it will stay high as long as it takes to send this byte over the transmit channel. And then when the transmission is done, the active will go low and done will go high for 1 clock cycle. And after that, the larger circuit can provide another byte if it's ready. So how is the receive circuit going to work? Down here in red, I suggested that it will be in several different states. In the idle state, it's waiting for the beginning of the start bit. And then in the start state, it has to wait until the middle of the bit. And then it will be in some state where it's waiting to receive the next bit. And finally, there's a stop state where it's waiting until the middle of the stop bit. So I've drawn a state diagram to reflect that. Okay, idle, start, get bit, and stop are the states in this finite state machine. So more precisely, let's look at what happens in the idle state. Basically, it stays in this state waiting for the RX input to go low to indicate the beginning of the start bit. And then it goes into the start state, and it stays in that state waiting for 1/2 of clocks per bit. Our clocks per bit value is 543, so we have to wait for 1/2 that number of clock cycles. And at that point, we should be in the middle of the bit. And then at that point, we proceed to the get bit state. And that will wait clocks per bit to get to the next bit, to the middle of the next bit. And at that point, it will get the bit. It will look at the RX input line, and it will capture that. We'll also keep something called the bit index, because we have to do this 8 times. And so then it will increment the bit index. And if it hasn't gotten to the end of the byte yet, it will stay in this state. It will also reset the counter, so it will wait another bit time before it samples again the RX input line. And finally, if the bit index has reached 7, that is, we've gotten all the bits, then we will wait 1 more bit time to get to the center of the stop bit, and that's what's going on here. And then finally, we will set the data available and data byte outputs high for 1 cycle and transition back to the idle state. So this finite state machine will need some kind of variable to determine what state it's currently in. We're also going to need a counter to count the time here. And we have a variable bit index, so we need to keep track of what bit we're waiting for. And so I've summarized all of the state of this machine down here. We have 4 states: idle, start, get bit, and stop. So we have a register with 2 bits for the current state. Then we have a counter, and we'll use 16 bits for that. We have a variable bit index, and for that we have a 3-bit register, which can range from 0 to 7. And finally, we have the data byte that we're accumulating. That has 8 bits, and the data available register. So we'll need to set that, and these are what will get output from this circuit.
So we'd like to describe this finite state machine with some Verilog code. Probably the most important Verilog concept is the module. A module will describe a circuit, and it's a large syntactic construct, sort of like a function definition. It has inputs and outputs, sort of in the same way that a function will have parameters. And then the module will have a body which describes the circuit itself in the same way a function definition would have some code within the function. A module is a little bit like a class in the sense that you have to instantiate it to actually use it. So you could have a class definition, for example, but in order to use that class definition, you'd have to create some objects that are instances or members of that class. Likewise, the module will describe a circuit, but if you actually want to have that circuit as part of a larger design, you need to instantiate the module. And a module can be instantiated one or more times. For example, if your module describes a full adder and you want to build an add unit, you would instantiate that full adder module a number of times, once for each bit position. So we can have definitions, sort of like we have variable definitions in a programming language. You can create a wire with a statement or declaration or definition that looks like this with a semicolon. So here's a wire called A. Here's another variation on that where you are creating an array of wires. So X refers not to one wire but to 8 parallel wires. You can also create registers, and here I'm creating a register with, in this example, 8 bits. These will be implemented with flip-flops. Combinational logic in Verilog is pretty straightforward. So you can take 2 wires like Y and Z and join them with a number of different binary operators, Boolean operators. And in this example, this would be implemented with an AND gate, and the output would be connected to the wire that we have defined that's called X. Now, if Y and Z are arrays of wires, then this will be a bitwise AND operation implemented with, in this particular case of 8 AND gates. And so this would be pairwise bit AND. Verilog also has a notation for expressing constant values or fixed values, and here we are showing that the constant can be defined in terms of binary, hex, or decimal. And this notation 8 apostrophe indicates that this is to be a constant with 8 bits. So this value here tells how many bits the value will have, and both of these, or all 3 of these, are equivalent. Now down here we have an example where we've got a bus or a wire with 8 individual components, and we are tying it to particular fixed values. So we're expressing the value one way here, and here we're expressing it in decimal. The decimal is assumed, and these things will both be 0 extended to the appropriate size here. These are equivalent, but obviously you would assign X to only one thing, whether it's the result of some combinational logic or tying it to fixed values. The input to the receive circuit is asynchronous, which means the transitions can happen at arbitrary times. We can say that the input signal is coming from a different clock domain than our circuit itself. And we have a problem. We might catch the input signal during a transition, and it might not be either a 0 or a 1. And so we have the problem of metastability. And I'm not going to go into that here, but one solution is to take the input signal and run it through two flip-flops. So here we have two flip-flops that are clocked by our own internal clock that kind of clean up the signal, if you will, and move it into a clocked signal in our domain. So I want to describe the Verilog construct always, and there are two forms of the always construct, and this is one of them, and it's kind of idiomatic, always at positive edge, and then our clock signal, and then we have begin, and then some stuff, followed by an end. Now within this always, we have a number of statements, and we're seeing this notation here, x gets, and here we've got something. This is not less than or equal. This is sort of an assignment, but it's an assignment to a register. So x and y are registers. And what this is going to do is set the register on the positive edge of the clock signal. And the right-hand side of these statements can be combinational logic, and it can involve the output of registers. So here, for example, y gets y plus 1. This will increment some register on every clock cycle. Okay, so now let's see how this circuit looks in the Verilog code. So here is some Verilog code, and it is for the module that describes our receive circuit. So you can see in green we have some comments, and in blue we have keywords. So the Verilog keyword module will be matched by an end module keyword, which is down below. We'll get to that. And this is a little bit like a procedure definition, in that procedure starts with some parameters and then has some local variables and then has some code. So this module, which we are going to be naming UART RX, has several input and output wires, and then it has some local variables, some registers, and then it has the code here. We see that this module will take several inputs and outputs. So these are the connections to this module. We have our input RX signal, we have a clock signal, and then we output 8 bits for the data that we receive, and the available line, which we clock high. So looking back to our diagram, we see the inputs and we see the outputs here. This parameter here is a compile time constant. This is our clocks per bit, which we said was 534, I believe. And then we also have some local parameters, which we define here. So these are just some constants. We then have some local variables, and in this case we have the state, okay, the state of this machine. And remember that our state had the 2 bits, the state variable, and then we had a counter, which was going to be 16 bits, and then we have the bit index, which is 3 bits, and finally we have the data byte, which we will use to store the accumulated data as it comes in, and that's 8 bits, as well as a 1-bit register called data available. We've also got 2 flip-flops, 1 bit each, and those are called RX buffer and RX. And here you're seeing those. That's this stuff here that will condition our input line. And so our state is 2 bits, and so we have some constants, and actually this should be a 2 here, okay? But these define the values for the idle state, the start state, the get bit state, and the stop state. So the outputs that we have are the 8 data bytes and the available line, and these will be connected to these registers here, okay? And that's what we're doing with this combinational logic here. It's not very complex combinational logic. Basically, we're just connecting the wires and identifying these wires as being one and the same. By the way, this notation where you see I and O for input and output is a common convention, It helps clarify which direction the signals are flowing. Okay, now we have the always at positive edge clock begin end idiom that we looked at before. And so this is the code that implements this circuit right here. Okay, so how does it work? Every time the clock goes positive on that positive edge, we will update these two 1-bit flip-flops, the RX buffer and the RX. So here you're seeing that right here. We update the RX buffer from the input line. Okay, that's happening here. And we update the flip-flop that's called just RX from the output of the RX buffer. And so that's happening here. And then later in our circuit, we will use the output of this flip-flop, which is called RX, and we will just, the output wire has the same name as the flip-flop itself, if you will. And so that's what the bulk of the circuit, the main part of the circuit, will actually use. So it will be the conditioned form of the input signal. In a programming language, statements are executed one after the other. But Verilog is not a programming language. It's describing a circuit. And so, in effect, these things are happening simultaneously. This is describing a circuit. And in Verilog, you could reverse these two lines, and it would build the same exact circuit and work exactly identically. So that's a bit counterintuitive. The code of this module goes on for 2 more pages, and you see at the bottom here we have the end module keyword. It looks pretty complicated, but it's not so bad. So what we've got here is another always at positive edge of the clock begin, and it goes all the way down here to the bottom, and it ends right before the end of the module. So this begin block has a single case statement, and again it has a number of cases: idle state, start state, and so on, stop state, and a default state, and then we have the end case right before the end. So what we're looking at is a giant case statement. And so on the positive edge of the clock, what are we going to do? Well, it's going to depend on the current value of the state flip-flop. And so our case statement has 4 branches plus the default branch: the idle state, the start state, and the get bit state, and the stop state, and then there's a default state. And each one of these has a begin and end structure. So then let's take a look inside of the idle state. When we're in the idle state, what are we going to do? Well, if we go back to our original picture of the finite state machine, the idle state basically is waiting for the RX line to go low. And so we will stay in the idle state. Okay, so if the state is idle state, we will reload state with the same value, okay, unless RX is not low, is low. And if RX is low, then we will load the state register with a different value, the value for the start state. Okay. In addition to setting the state register, we will also set these other registers. We will set the bit index, the counter, and the data available registers to 0. So that's the idle state. Next, let's ask what happens when the clock goes positive and we are currently in the start state. Well, it's tempting to say we execute this code here, but remember, Verilog is not a programming language. It's describing a circuit. So all of this code is basically describing how to load the registers depending on the previous values of the registers and other combinational logic at the rising edge of the clock. So we have a number of registers being loaded here. So if the previous value of the state register is start state, then we're going to load these registers as we specified here. Now we're not actually loading the data available register or the bit index register. So in that case, those registers will retain their value. They will not be loaded with anything different. Okay, so let's take a look at this. We are looking at the counter, and if it has reached the halfway point, clocks per bit is a constant, and we are dividing it by 2 here. And if the counter has reached that value, then we're going to load the registers as we specify here. Otherwise, we're simply going to increment the counter, and so we see that happening here. And we are going to remain in the start state. I suppose we don't actually have to specify this line here, but I think it makes it clear what's happening. On the other hand, if the counter has reached the halfway point, that means we're in the middle of the start bit, then we check the input line again, and if it's still low, which it almost certainly will be unless we had some kind of a glitch or something weird is going on, then what we're going to do is reset the counter to 0 and change the state register to the next state, the get bit state. If for some reason we had a glitch and the RX value is not still low, then I'm not sure exactly how that would happen, but something's going on. So we immediately go back to the idle state and hope that we can get squared away. Perhaps we could have some noise at startup time or something like that. Okay, let's move on to the get bit state. In this state, we're either waiting to reach the halfway point in the middle of the bit or not. So we check the counter first, and if the counter is less than the halfway point, then we will simply increment the counter. And of course we stay in the same state, so that's indicated right here. However, when the counter reaches the halfway point, that is, we've gone one full bit period, and we are now in the middle of the first bit or the second bit or whatever, we need to reset the counter and store the current bit. So we sample the input line, Rx, and here we see the power of Verilog. We are moving into the bit of this 8-bit register that is indicated by the value of this other register. And then we check to see whether we are at the last bit. Okay, we look at the current value of the bit index, and if we just store it into 0 through 6, that is less than 7, then we will increment the bit index register and stay in the same state. On the other hand, if bit index is now 7, then we can reset it and move to the stop state. So after we store the final bit, at this point right here, we need to wait one more bit time to get to the middle of the stop bit. At that point, we can go into the idle state and start watching for the high to low transition that will indicate the beginning of the next start bit and the next byte. We can't immediately go into the idle state at this point because we might very well already be at a low level, and so we could get confused. So we need to wait one bit time to get to here, and that's what's happening in the final case in this case statement. So if we're in the stop state, we take a look at the counter register, and if it has not yet reached this maximum value, then we simply increment it and remain in this state. On the other hand, when we have reached the middle of the stop bit, then we will set the data available register to 1 and return to the idle state. We're also setting the counter to 0, but I don't think that's actually necessary. I think that's redundant, because in the idle state we will immediately set the counter to 0. But in any case, we are setting the data available register to 1 in the stop state. So on the next clock cycle, it will remain 1 for one clock cycle. And then on the next positive edge of the clock, when we are now in the idle state, it will then be lowered back to 0. So that will give us our 1 clock pulse of the data available register. Finally, we have a default case down here. I think we've handled all the cases, so this is not strictly necessary, but it's probably good programming practice. Okay, well, this circuit actually works. I've run it on an FPGA, and so the code that I've shown you is, in fact, working Verilog code. So now let's look at our design for the transmit circuit. We will have 2 inputs. One is the 8-bit byte that we want to send, and the other is this line data available, which will go high to indicate that we have a byte on this input and that it's time to send something out on the transmit line. So the data that is provided will go high for only one clock cycle, and the data available line will go high to indicate that we have valid data. Our circuit will need to latch this data into a register and keep it there for the duration of the transmission. While the transmission is occurring, this output line called active should be held high, and then at the end of the transmission, the done output will go high for one clock cycle. So here's a finite state diagram to show what we're going to do. We're going to have four states: idle, start, send bit, and stop. We'll stay in the idle state waiting for this data available input to go high, and at that point we'll start sending, and we'll go to the start state. Here we will send a 0, which is the start bit, and we will wait in this state for clocks per bit. That is, we'll wait for one full bit time. After the start bit is sent, we'll go into the send bit state, and it will send the next bit, and it will stay in this state for one bit time, that is for clocks per bit, and then if this was the last bit, it will transition to the stop state. Otherwise, it will increment a register called bit index, reset the counter, and stay in this state and send the next bit for one bit time. After the last bit is sent, we'll transition to the stop state. We'll stay here for another bit time, sending a 1, which is the stop bit, and at that point we'll go back to the idle state. Here are the registers that will contain the state. First of all, we've got the state: idle, start, send bit, or stop. So we have a 2-bit register for that. Then we have a counter, and we'll use 16 bits again for the counter. Then we've got a register called bit index, which will range between 0 and 7. Then we've got a register called data byte, which we'll use to latch in the input byte that we want to send. And finally, we have 3 more registers: O active, or output active, output done, and the output for the transmit signal. And these registers will be tied directly to the outputs of our circuit. So here is the system Verilog code that describes our output circuit, and it's in a module which we're calling UART-TX. It has some inputs and some outputs. If we go back to our picture, we can see that the inputs are clock, the data byte, and the data available line. And the outputs are the transmit line, active, and done. The transmit line, the active, and the done. We're using this convention of prefixing the variable names with I and O to indicate whether they are input or output. And here we see that the inputs are simple wires, but the outputs are not wires but registers. So we will be setting these registers, and the output of the register, or the value of the flip-flop, will be the output of the circuit itself. We have a parameter, an input parameter, which is this clocks per bit, which is a constant value, as well as some local constants for each of the various states. In our circuit, we will have the following registers: state to indicate what state the finite state machine is in, counter, bit index, data byte, and the 3 outputs. And we're seeing those here: the state, 2 bits, the counter, 16 bits, the bit index, which is 3 bits, and the data byte. This is where we are latching the input data byte, I data byte. And the remaining 3 registers are shown up here. Here is the code for the body of this module, and you can see that it ends with the end module keyword. And like the receive circuit, it consists of an always block with a big case statement. So on the positive edge of the clock, we're going to look at the previous value of the state register and do one of 4 things. So we have a case for the idle state, and then down here we have the start state, and then continuing on the next page we have the send bit state, and finally the stop state, and we also have a default down here. And that's all there is to this module. So let's start by looking at the idle state. If on the rising edge of the clock, the state is in the idle state, then we take a look at the data available input. And if it is high, then the next value of the state register will be the start state. That is, we'll move into the start state next. Otherwise, we'll stay in the idle state. If we are going into the start state, then we will also latch into the data byte register the 8 bits of input. And so we'll capture the input byte. And we'll also raise the active output line by setting this output active register, or flip-flop I should say, to 1. Now we will also, regardless of whether we're going to stay in this state or not, we will keep the transmit line high. So while we're in this idle state, the transmit line will be high until we're actually ready to start sending the start bit down here. And we'll also have the done bit being low. We reset the counter and the bit index. Now this code doesn't have this line in it, but I've added it since. And we really ought to set the active register to 0 at this point if we remain in the idle state. And why is that? Well, conceivably on power up, this active register could be high, and then it's latched in the high state. And we're in the idle state with the active being high. And if that situation were to arise, then the larger circuit would see that the active line was high, and it would never try to send a data byte to it, so it would never raise the data available line, and we could get stuck in this idle state, in this weird state. So I've since added this line, and it worked without it, but I think it's better to have this. Okay, let's move on to the start state. In the start state, we're going to be sending the start bit. So the first thing we do is we set the TX flip-flop to 0. Remember that the start bit is a 0. And then we use our counter. So we check to see whether the counter, which was set to 0 back when we were in the idle state, we check it to see whether it has reached its maximum value. And if not, then we increment the counter on each clock pulse and remain in the start state. And once the counter has reached the maximum value, we reset it and move on to the send bit state. Once we're in the send bit state, we're going to start sending the data bits, and we will remain in this state until all 8 bits are sent. We're going to use the bit index register as an index into the data byte register and use that value to set the output line. Then we look at the counter register, or really simultaneously on the same clock pulse, I should say. We're looking at the counter register to see whether it has reached its maximum value. And if not, we will just increment it by 1 and remain in the send bit state. On the other hand, if the counter has reached its maximum value, then we will reset the counter on the next clock pulse and also look at the bit index register. And if that is less than 7, then we need to do one more bit. So we'll increment it and remain in this same state. And that way we'll go around and on future clock pulses, we'll send the following bit. However, if bit index has reached 7, then we're done sending all of the bits. So here we reset the bit index to 0. And that's not strictly necessary because we would do that in the idle state anyway. But we now go to the stop state, where we will be sending the stop bit. We will remain in the stop state while we're sending the stop bit. Recall that the stop bit is 1, so we need to set the TX flip-flop to a 1, and we do that here. And then, or simultaneously, we're also looking at the counter. And if it has not yet reached its maximum value, then we will increment the counter on the next clock pulse and remain in the stop state with the TX output being high. Otherwise, if the counter has reached its maximum value, we'll set the done flip-flop to 1. Remember that the done output line has to go high for 1 clock cycle. and at the same time we'll clear the active flip-flop and move into the idle state. So when we're in the idle state, the done bit, which we set to 1 here, on the next clock pulse will be set back to 0. So this has our pulse for the done line. So next, let's answer the question of what is a field programmable gate array. Well, an FPGA is just an IC chip with a whole lot of gates and a whole lot of wires, but it is configurable, so we can program in the circuit we want. So in the example I'll look at, we'll use a NAND gate. It turns out that the NAND gate is very general, and you can build any digital circuit out of only NAND gates. So here is an example of a field programmable gate array. It has a gigantic fabric, a huge array with lots and lots of gates and lots of wires. But these intersections here are not connections, they are potential connections. So in order to put your circuit into this array of gates, you're going to need to program it. You're going to need to make the connections. So here where I've drawn a dot, I want the connections to occur. And so in that way we can build up a circuit. So each connection, or I should say each potential connection, is implemented with a 1-bit latch. It can be in one of two states. Either there is no connection there, or there is a connection there. And so to program the FPGA, we simply download a huge bit string that corresponds to all the potential connections, and then that creates the circuit that we want. And this list of all these potential connections, this big bit string, can be kept in flash, and so you can see why we can call it a field programmable gate array. Now I've shown an example with just NAND gates, but in reality NAND gates are really too simple, and there's a lot more on the FPGA fabric than simply NAND gates. For one thing, we can have other kinds of gates, but we will also have things like adders and maybe multipliers and bigger circuits. We will also see flip-flops or register arrays or even a large memory array. And in fact, we might have an entire processor core fabricated on the IC along with the gate array so that we can use that rather than having to program in the processor. And so this makes the FPGA a lot more functional, and you can get a lot more stuff onto a single chip this way. So in order to use an FPGA, we need to create a design, and that goes into the Verilog file. And then when we go to compile it, what happens? Well, the development environment will parse the Verilog file or files, and from these it will construct the circuit. And then there are several more steps. The fitting step is where the development software will map the circuit onto what's available on a specific FPGA chip. So you need to tell the development environment what kind of chip you're working with, and some have different kinds of things. It might have multipliers, or it may be a chip without any multipliers, and so on. So that's fitting, where it fits your circuit onto what's available on a specific FPGA chip. And then the development software can run a timing analysis to make sure all the setup times and the hold times and so on meet the specifications so that the thing should work. And then finally you want to download the design to the FPGA chip and then of course power it up and use it. I've got a demo coming up, but before we do that we have to instantiate the two modules that we've created. We designed a circuit for the receive side and for the transmit side, but those modules are essentially templates. We need to instantiate those modules in order to get a copy of the circuit. And when we do that, we also have to say how that module will be connected, how we will connect them together, or how we will connect them to the external pins on the chip. And that's what I'm doing with this code right here. This code is part of a larger module, and I'm not going to show that, but it shows how we can instantiate a module. So this bit right here is where we're instantiating the receive module, and we're going to give it a name here. And here we're instantiating the transmit module, and we'll give it a name as well. And what we want to do is we want to hook the receive module to the transmit module. So every time a byte is received on the input channel, it will just be echoed on the transmit side, and that way we can evaluate the circuit to see whether it's working or not. Now, when you call a function in a typical programming language, you provide the argument values, but you don't provide the names of the parameters that are used within the function. With circuits, sometimes we have lots and lots of connections. So here we actually do provide the names that we are using internally to the module. So these are the names that we used within our definition of this module, and these are the names that we used within the transmit module. They don't have to be in order, so you can change these around if you want to, but this helps keep things straight. And this shows how it's important to use this convention to differentiate between inputs and outputs. Okay, so we've got the instantiation right here, and here with this part right here we are providing a value for this parameter, the clocks per bit. Well, that's 543 cycles for each bit time, and we're providing that number so that it can be used when this module is instantiated. And now the receive unit has a number of, it has two inputs, clock and the receive line. And I'm hooking the clock to some wire called clock fast. I'm not showing that here, but that's our system clock. And I'm hooking the receive input wire to something that corresponds to a pin on the chip. And I'm not showing that either. Likewise, down here with the transmit, I'm hooking it to the clock and to another pin on the chip. I've got a few wires here. Let's look at this data available wire. It's an output from the receive unit. So here I am connecting the output data available to this wire, okay? And then I am running that over to the transmit side, if you will. And here I'm using that same wire and providing it to the input. So when the receive line raises this available line, it will have the effect of raising the available line to the transmit unit and start a transmission. I'm not going to be hooking up the outputs called active and done for the transmit. We'll just kind of ignore those, so I haven't provided anything here. And here we have a bus with 8 wires, okay, called data 8. And that is the output from the receive unit. And what we're going to do with data 8, we've also got this other bus called data plus 1, is down here I have some combinational logic. What I'm doing is just simply adding 1 to the data 8 wire or collection of wires. And so this is being computed, and then we will provide data plus 1 as the input to the transmit unit. And so what this is going to do is when a particular character is received, such as an A, it will add 1 to the ASCII code, which would mutate it into a B, and then that will be provided to the transmit unit. So that will allow us to check that we really truly are echoing. And it also shows that we can have combinational logic. It shows that this is a specification. I put this combinational logic down here below this stuff, but the order doesn't really matter because all of this stuff is really just describing a circuit and it's not being executed in order. Okay, now let's take a look and see how this works. To develop code for an FPGA, you'll need to use a development environment. This is the Intel Quartus development environment. This is a very complex piece of software, but once you get everything set up, you can just go up here and press this compile button to compile your design and prepare the files for downloading. I've got a board right here. This blue chip is an FPGA, and there's some other stuff that we can ignore, but let's go ahead and turn this on. Then, when we get ready to download it, we go to this other Quartus window and press the Start button here, and that will begin the download. You'll see a little LED go on when I press the button, and that indicates that it's now downloading to the FPGA. And then when it's done, we'll go ahead and test our software, our Verilog design. So Here I've got an app called CoolTerm, and this is just a little serial monitor. And so when I press a key, I'll go ahead and press this B key here. Let's see what happens. We get a C. And if I go ahead and press the G key here, we get an H. So you can see that every time I send a character across to the serial communication circuit, it will add 1 to it, that is G becomes H, and then send it back over the other channel. So it looks like our circuit is working, and that means that this is the end of the video. Thanks very much for watching. I'll see you in the future.